Today we're going to be talking about moving loads. Now, a moving load refers to any load that changes its position over time on a structure. This is opposed to a static load which remains in a fixed position. Now, in engineering, engineers must consider moving loads when designing structures like bridges, roads, and railways to ensure that they can safely carry vehicles, trains, and other dynamic loads without excessive deformation or failure. This is because moving loads cause varying stress distributions and potential maximum stresses at different points in the structure. Now, relating this to the real world, this is usually found in bridges wherein moving loads from vehicles and trains will require complex design considerations to maintain safety. However, this is also found in elevators and cranes, wherein the moving loads in elevators and cranes need precise calculations to prevent any unwanted situations. And then for roadways and pavements, the effect of moving traffic loads on pavement design is critical for ensuring durability and performance. Now, in strength of materials, we're going to focus on the application of moving loads, particularly in bridges, because it's the most common application. Now let's say we have this situation. A truck with axle loads of 50 kN and 30 kN on a wheelbase of 2.5 m crosses a 10 meter span. Now we have to compute the maximum shearing force and the maximum bending moment. Now these axle loads refer to the wheel loads. Essentially, a truck consists of a distributed load. However, it is reduced into axle loads so that it will be easier to analyze. And then almost always, the larger load is at the rear end, not at the front end. Now this is because items that will be delivered are on the back side. And so that's why in this example, to make this more realistic, the larger load is on the rear end, not here. The driver must be so heavy in order to change the configuration. However, in some cases, the smaller load is on the left side. Now this is because our truck can move in two different ways. It can move this way, or when it goes back, let's say it has finished delivering items, it will now go back. And so the front end will be right here, and then we have here the rear end. And so it's gonna look like this. Now let's just erase this one. And so again, it's important to be able to know the maximum shearing force and the maximum bending moment that will occur on the span, because that will govern our design consideration. Now let's try to draw lines wherein we'll establish the shear diagram and the moment diagram. And then let's just say that the truck right here will move slightly to the right. Now we have this configuration. Let's say that it has moved 1 meter from point A. Now if we're going to solve the reaction, by the way, this is our span. This is the bridge. And then we have point A and point B. And then we'll assume it to be simply supported. And so that's why we have vertical reactions right here. Now to solve the reaction at A, I need to take moments about B. And then if I'm going to draw the shear and moment diagram, we have this one. Taking moments about B, we have RA, the reaction at A, multiplied by the moment arm, which is 12, and then minus 30, our smaller load, which is already on the span, multiplied by the moment arm, which is 11 meters. 12 meters minus 1. And so that's why we have 27.5. And then to get RB, we can take moments about A, or we can sum up forces vertical. Now to make it more efficient, let's just sum up forces vertical. And so we have RA minus 30 because it's acting downward, and then plus RB, that's equal to 0. So we have here RB equals 2.5 kN. And so drawing the shear diagram, we only have concentrated loads. But again, this load, the one provided by the vehicle, that's actually a distributed load. But again, we are reducing it into concentrated loads so that we'll be able to locate the point of maximum moment easily. And so here we have from 0, again, we always start from 0. We're going to move up 27.5 because of the reaction, and then we're going to use a straight line because there's no loading right here, and then it remains constant. And then at this point, we're going to subtract 30. And so from 27.5, we have 27.5 minus 30. That's equal to minus 2.5. So this is actually negative. So we're going to move down because we have a concentrated load. And then from this point up to this point, we have no loading. So that's going to be a straight line. Just follow this one. Now for the moment diagram, again, this is a positive constant line. And so we have here an ascending line, which is 1 degree. Because again, we have 0 degrees right here, plus 1 for the moment diagram. That's going to be 1 degree. And also right here, this is 0 degrees, and this is 1 degree. Now the value of the moment at a point is the area of the shear diagram from a certain point to a point of interest. And so if I'm going to solve the moment right here, which is our maximum moment, I need to get this area. And so that's going to be, this is only a rectangular area, so we have 27.5 multiplied by 1 meter. And so this gives us 27.5. And then this is kilonewton meter. And so this is our maximum moment for this configuration. However, if you're gonna think of it conceptually, this configuration will naturally not be able to give us the maximum moment and the maximum shear. Now this is because the 50 kN load is still not on the span, and so the moment values and the shear values will be lesser. Now what if we're gonna move the truck inside the span, such that the 50 kN load will be at this point? This is what will happen. Our shear diagram and moment diagram are gonna change. Now let me just go over the solution. To get RA, we need to take moments about B. So we have here RA times 12. Again, this was initially unknown. So RA multiplied by 12, the moment arm going to B. And then that's plus because it's gonna cause a clockwise rotation. And then for the 30 kN load, we're gonna use minus because if this is our moment center, or if you're holding that point, and then you're applying this load, your beam will rotate counterclockwise. So that's why we have minus, and then our moment arm going to B will be 8.5. Now sir, where did this come from? To get 8.5, we have 12 minus 1 minus 2.5. That's how we can get this distance. Again, this whole distance minus this one, and then minus the distance between wheel loads, we have 8.5. By the way, the distance between wheel loads is also called wheelbase. And so this is something we have to remember. And so again, we have minus 30 times 8.5. And then we have 50 multiplied by 11. Now this 11 comes from 12 meters minus 1 meter. Now solving RA, we have 67.083. And then summing up forces along Y, we're gonna get RB equals 12.917. Now forming the shear diagram from 0, since we have a concentrated load, we have left and right shear values. From 0, we're gonna move up 67.083, which is the reaction at A. So from 0, again, we're gonna move up, and then we're gonna draw a straight line because we have no loading at these points. And then right here, we have 50 kN going downward. So from 67.083, we're gonna subtract 50 kN, and so we have 17.083, this one. So we'll move down, and then since there is no loading at these points, we're gonna use a straight line, and then at this point, we have the 30 kN load. And so to get this value, we have the left shear value, which is 17.083, simply this one, and then minus 30 kN. So minus 30, we're gonna get this value, and then we'll move down, and then it's below the 0 line because this gives us negative. And then from here up to here, there's no loading, so we're just gonna draw a straight line. And so we have this one. And then finally at this point, we have 12.917 going upward. And so we're gonna move back to 0. Now for the moment diagram, this is positive constant, this is also positive constant, while this is negative constant. And so that's why here we have an ascending line, and then here we also have an ascending line, while at this span, we have a descending line, which goes down until it reaches 0. And then by the way, the degree of these curves is 1 degree, because again, these are constants, so its degree will be 0. And then plus 1 for the moment diagram, we have 1 degree. Now to get the moment value at this point, we need this area. And so that's why we have here the moment under the 50 kN load is 1, this distance, multiplied by 67.083. So we're gonna get 67.083. Now how about for this point, the moment under the 30 kN load? To solve that, we have the left moment value, which is 67.083, and then plus this area. Now this area is 17.083 multiplied by 2.5 meters. That's why we have this. And so adding both, we have 109.7905. And so this is the moment under the 30 kN load. Now in analyzing maximum moments, it's usually gonna occur directly under our loads. Like for example, for this configuration, the maximum moment occurs under the 30 kN load along this line. So that's what we're gonna solve. However, as engineers, we are interested in the maximum moment because it will govern our design. We're not interested in configurations that are safe. We are interested in what's unsafe because that's what we're gonna try to counteract. Now let's say we're gonna move the truck further. Let's say instead of 1 meter from the left, let's move it 2 meters. Now we have this one. As you can notice, the moment under the 30 kN load has increased, as well as the moment under the 50 kN load. Again, here we have 67.083, and then for the 30 kN load, we have 109.791. But moving the truck 2 meters from the left support, we're gonna increase the values. So we have here, the moment under the 50 kN load is already 120.834. While here, for the 30 kN load, the moment under it is 146.8765. And so it's significantly larger. Now what if I'm gonna move it further? By the way, for the solutions, just try to look at the figure since all the explanations are just the same earlier. And then these are simply the areas of the shear diagram across 2 points. And so again, what if I will move this further? This is what happens. The moment is still gonna increase. However, as you can notice, the maximum shear has constantly decreased. If you'll try to look at the previous one, we have 53.75, and then here we only have 36.875. And then for this configuration, we have 33.75. By the way, this is 60.417. Let me just change it. So again, from 27.5, we had 67.083 when we moved the loads inside the span. And then if we're going to move it further, the maximum shear will decrease. So we now have 60.417, and then it's going to be 53.75, and so on. However, the behavior of the moment will not necessarily follow the behavior of the shear values. That's also a concept that you have to remember. I will just be discussing later on what configurations you can form the maximum shear, and on what configurations you can form the maximum moment. Now again here, the moment has increased. From 120.834, it has become 161.25, and then here it has become 170.625. Now, since I have solved this beforehand, let me just show you first the configuration wherein the maximum moment will occur. Now we have this one. Now for 2 moving loads, the maximum moment will always occur under the larger load. Now in our earlier situations, the larger moment is under the 30 kN load. And so that's why here we have 170.625, but it's not under the 50 kN load. And so that's not going to provide the maximum moment. However, in this configuration, the maximum moment is already under the 50 kN load, which is 203.96. While for the 30 kN load, it's only 171.152. Now I will be discussing later how you can get this value. However, in our previous video, I already showed how to get this value using calculus. However, in this particular lesson, we're gonna talk about the conventional method, which is the application of Vergnon's theorem. Now, I will just show you that later. Now again, this distance is obtained by calculus, but there is another way to get that. Now, once you get this value, 5.53125, you're gonna use that to solve the maximum possible moment given the wheel loads, which is simply the area under the shear diagram. And then by the way, as you can notice right here, we have positive and then positive in between these loads, but for the configuration of the maximum moment, the behavior of the shear diagram actually changed. We now have positive, and then this one is negative, and this is also negative. However, the value of the maximum shear actually still decreased. From 53.75, we now have 36.875. Now, since this is negative constant, we have here a descending line. And so that's what I meant earlier, that the behavior of the moment diagram will change due to the shear diagram changing. But then again, for the shear values, we have noticed that the shear value constantly decreased as we move the truck further. And so that's going to be important later. Now, how do I know that this is actually the maximum moment? Let's try to move the truck further to the right, and then let's try to see how the moment value will change. If we're gonna move the truck, let's say something greater than 5.53, let's say 6 meters, we now have this configuration. Now, as you can notice, the shear value continued to decrease, and then the moment under the 50 kN load is still the larger moment value compared to the moment value under the 30 kN load. However, it has decreased to 202.5 instead of 203.96. Now, if you're gonna move this further, that trend will still follow, and so that's why we are sure that the maximum moment occurs when this is our situation. Again, at a point lesser than 5.53, the moment under the 50 kN load was 161.25. And then here we have 203.96, and then for a point beyond 5.53, the moment under the 50 kN load actually reduced. It has become 202.5. And so we're going to discuss how to solve the maximum moment and the maximum shear. Now, for the maximum shear, I hope you would agree that to get the maximum shear, the larger load must be over the support. The farther away this load is from the support at A, the smaller the shear value, as you can see from our discussion. Again, when this load is 6 meters from A, we have a shear value of 33.75. But when it's closer, we have 36.875, and then let's bring it closer, we have 53.75. And so naturally, the maximum shear will occur if this load is directly over A. And so here, the maximum shear occurs at the support when the load nearest the resultant force of the moving loads is placed directly over the support, provided that all loads are still on the span. However, for overhanging beams, the maximum shear will occur at a condition where the loads are placed at the tip of the overhang. Now, I will just be discussing this in another video. And so, we're first going to discuss what this means when the load nearest the resultant force of the moving loads is placed directly over the support. Now, there are two things here. We have the resultant force and the load nearest to it. By the way, this refers to the extreme load. Now sir, what do you mean by extreme load? These are loads on the leftmost part and the rightmost part. Like for example, for this one, this is the leftmost load, while here, this is the rightmost load. That's what we call the extreme load. Now what if we have three moving loads? Let's say this is 20, this is 10, and this is 5. What will be the extreme loads? Let's say the distance separating them is 2 meters and 1 meter respectively. This will be your extreme load, the leftmost load, and also this one. That's the rightmost load. And so this is important for the maximum shear because the maximum shear is likely to occur if all of the loads are still on the span. Because if let's say this was 30, if you will place this over the span, let's say right here, let's just draw another one. Let's say we're gonna place 30 right here, and then we have 5 separated by a distance of 1 meter. Notice that with this configuration, although the largest load is over the support, let's say this is point A, we have a support right here, and this is RB. Now, although the largest load is directly over the support at A, notice that with this configuration, the 20 kN load will actually be outside the span, and so it won't be included in your calculation of the maximum shear, and therefore, your maximum shear will be lesser. And so that's why we're always interested in the extreme loads, so that all of the loads moving along the span will be taken into account. And so this is something you have to remember. I will just include an example for this one. And so going back, we're first going to solve the resultant of these forces. Now how are we going to get that? We're going to use Vergnon's theorem. Now we have here, since we are interested in horizontal distances, we have the resultant force P multiplied by barred X. This is equal to the summation of Pn and then barred Xn. Now don't be confused by this one. This is just the same with the computation of centroids or the center of gravity. However, instead of areas, we are dealing with forces. And so for P, we're gonna sum up all the forces, and then for Pn, we have each of the loads, and then for barred Xn, we have the distances of each of the loads from the reference axis. Now let me just redraw this one. We have 50 kN, and then we also have 30 kN, separated by a distance of 2.5 meters. That's our wheelbase, or the distance separating the moving loads. And so this is 2.5 meters. Now we're first gonna solve the resultant force. We have P, which is simply equal to, let's just sum up forces vertical. The resultant force will be 50 plus 30 kN. So 50 plus 30 gives us 80 kN. And so we have here our resultant force. Now the question is, where is exactly the location of this resultant force? Now to get that, we need to first have our reference line. Now to make things simple, it's helpful to situate your reference line at the leftmost part of the load. And so this is my reference line. And so I'm interested in this distance, the distance from the reference line up to the resultant load. And so this is going to be barred X. And then we have here P, which is equal to 80 kN. Now applying this formula, we have P, which is 80, this one, multiplied by barred X. This is equal to Pn Xn. Now for the first load, we have, let's just label it right here. We have P1 equal to 50. And then the distance from this load to the reference line, that's going to be 0. Because again, this load is directly along the reference line. So we have 0, and then for P2 we have 30 kN, and then the distance from this load to the reference line is 2.5 meters, that distance. So we have here barred X2 equals 2.5. And so if we're gonna pair that, we have 50 times 0 plus 30 times 2.5. And so solving barred X, we have 0.9375, and so this is 0.9375, and so the remaining distance will be 2.5 minus 0.9375, which gives us this distance is 1.5625. Again, this is from 2.5 minus 0.9375. Now, it's easy to notice that the resultant force is closer to the 50 kN load. Now, this is always the case if we only have 2 moving loads. But for 3 moving loads, there are gonna be changes. Now again, the maximum shear occurs at the support when the load nearest the resultant force of the moving loads is placed directly over the support. Again, here, we are referring to the extreme load. Now, since this is the leftmost load, we have 50 kN, and then it's closer to 80 kN, which is our resultant force, then this means that we're gonna place this load over the support at A. And then the reaction at A will be our maximum shear. And so solving the reaction at A, we can take moments about B. So we have the summation of moments about B equal to 0. This is gonna be, let's say this is RA. We have RA multiplied by 12 meters, which is the moment arm going to B, and then we have 50 multiplied by the moment arm going to B, and so that's still gonna be 12. Again, that's the perpendicular distance going to B, so minus 50 times 12, and then minus 30 multiplied by the moment arm, which is 12 minus 2.5. So 12 minus 2.5, we're gonna set this to 0. Solving RA, we get 73.75, and then this is Kn. And so this is our maximum shear. Now, a few students might argue that if the 50 Kn load is directly over the support, it's not gonna provide this maximum shear. Now, there's a point in that, but I will demonstrate why the maximum reaction will just be equivalent to the maximum shear. Let me show it right here. Again, this was our beam. Now we have a 12 meter span, and then we have a 50 kN load and also a 30 kN load. And then this is over the span, and so the distance between the two loads will be 2.5 meters. Now a lot will argue that 23.75 is the shear value when the 50 kN load is over the support. However, you have to take into account that we have here opposing loads, and so we have a left and right shear value. However, to make sense of this fully, this 23.75 you are seeing, that's a net force. And so that won't necessarily describe the maximum shear. Let's try to move this to a value very close to 0. Let's say 0.00, let's use 7 zeros, 0, 3, 4, 5, 6, 7, and then 1. Let's use this instead, and then we're also going to move this one. Let's use again, we have 0.5 and then 6 zeros, and then 1. Notice that here we have the maximum shear equal to 73.75. This is actually the maximum shear that we want. However, since this will just be virtually equal to the reaction at A, when the 50 kN load is over the support, then we're just going to use this one for design purposes. And so we have to make that clear. Again, we now have here 73.75. But again, if you're going to place this directly over the support and then you will draw the shear and moment diagram, the value here will not be able to reflect the maximum shear. And so I hope that's clear. Now again, if you're going to move this to the leftmost part, you will actually have 23.75. But this is now erroneous. And so it's helpful to use the maximum reaction as the maximum shear. Now, if you have this app, you can actually move the loads anywhere if you want to explore concepts. And then you have here the shear diagram, the moment diagram, and then for structural theory, you have the slope and deflection. Now, I will just add more tutorials on how to use this app, because here, you can actually add springs using this one. Just input the spring constant right here, and then you're good to go. Now let's go back. We are now going to learn how to solve the maximum moment. Now for the maximum moment, it occurs under the load of interest. Now it may be the 50 kN load or the 30 kN load. But for two moving loads, the maximum moment always occurs under the larger load. But for three moving loads, that's not always the case. You have to check the moment under the three loads. Now for the maximum moment, again, it occurs under the load of interest. And then for the positioning, to be able to determine where we should position the chuck to produce the maximum moment, we have to situate the center of the load of interest and the resultant load at the center line of the simply supported beam. Now to better understand this, let's try to isolate our moving loads. And so we have this one, and then we'll first establish the center line of the beam. Now that's simply at the midspan, or right here at 6 meters. And so for this beam, we have 12 meters, half of that is 6. So this will be our center line. And then it's usually called CL. And so again, this is 6 meters. And then we're gonna write again the location of the resultant, which was again 80 kN, 50 plus 30. Now we have board X equal to 0.9375. And so it will be this distance. Now that we have this, again, this is the location of the resultant load, so we have 80 kN. Now again, we have to determine the center of the load of interest and the resultant load. Now this is our resultant load, and then we are interested in the moment under the 50 kN load, so we're gonna establish their center. Now considering these two, the center will be right here. Again, this is midway between the 50 kN load and the resultant. And so this distance will be half of 0.9375, which is 0.46875. Now after determining this one, we have to situate this green line, or the center of the load of interest and the resultant load, at the center line of the beam. And so we're gonna move this line right here so that we'll be able to determine the location of the moving load, which will produce the maximum moment. And so situating this green line at the center line of the beam, we have this one. Now this was the green line, it's already along the center line, and so now we'll be able to solve this distance. Now that's simply the center line of the beam is at 6 meters, so we have 6 meters minus this value 0.46875, that will be this distance. So 0.46875, we have 5.53125. And so this must be the location of the 50 kN load from the support at A to produce the maximum moment. And so we have this situation, and then once you will be able to determine this value, then you can now solve the moment under the 50 kN load. And so that value was solved earlier. Again, we have this one, 203.964. That's simply this area. However, so that you won't need to form the shear diagram, just take moments about the 50 kN load. And so to do that, just solve RA and then take moments about this load. So you have 36.875, your load, multiplied by the moment arm going to the 50 kN load. That's your maximum moment. And so that's why this is the load times the moment arm. Now, what if the question is, what is the maximum moment under the 30 kN load? This is what we will do. We already know the location of the resultant force. We have again 0.9375. Now this is our resultant force, which is again 80. And so this remaining distance will be 2.5 minus 0.9375, which gives us 1.5625. Now getting the center of this load and the 30 kN load, we have this line. And so this distance will be half of 1.5625, which is 0.78125. And so we must situate this green line at the center line of the beam so that we'll be able to determine the maximum moment under the 30 kN load, because it is sometimes asked in your quizzes in mechanics. Now we're going to situate the green line at the center line. We have this one, and so this is the resultant load. Now here, we'll make it clear that the configuration for the maximum moment is different for the configuration that will produce maximum shear. That's what you have to remember, because some students will form the configuration of the maximum moment and then solve the reaction at A, and then they will treat it as the maximum shear, which is now wrong, because for the maximum shear, you have to do what we did earlier. Again, the maximum moment and the maximum shear have two different configurations. And so with this one, we have the following distances. From the 50 kN load up to the support at A, that distance will be 6 meters minus 0.78125 and then minus 0.9375. So that will give us 4.28125. Again, this comes from 6 minus 0.78125 and then minus 0.9375. And then from this side, from point B up to the 30 kN load, we have this distance, 5.21875. Now, by the way, if you have the resultant force, you can actually just use the resultant force in solving the reaction at A and the reaction at B. Now, to demonstrate this one, let's go back here. Now again here, we have RA equal to 36.875. Now we can solve this value just by using the resultant, so that we'll only be using a singular force, not two forces. Again, let's go back here. Let's try to solve RA just by using our resultant force. Now we have here 80 kN. This is our resultant force. And so we can actually solve RA just by using this one. You can exclude the following. However, this only works for the maximum moment, not for the maximum shear, because you can't actually convert it. And so here we have RA. By the way, to solve RA, we need to take moments about B. So we have RA multiplied by 12, and then minus 80, this one, times the moment arm going to B. Now it will be this distance. Now again, this is 6 meters from the center line of the beam going to B. And so this distance will be 6 minus this distance, which is still 0.46875. And so this is 6 minus, again, this is 0.46875. Now we're gonna write it here, and then we're gonna set this to 0. Now as you can notice, our solution is more efficient because we are only using one load instead of two loads. And so we only need to use one moment arm instead of two. Now solving RA, we have 36.875, and then this is Kn. As you can notice, this is the same with our result earlier. Now if we are to check, we have this one, 36.875. But in our solution right here, we actually used two values. We have 30 and 50. But for our alternative, we only used the resultant load. And so this is better to use when you are solving the maximum moment. Because once you have RA, you can just multiply it by the moment arm, which is again this distance. This was 5.53125. Now multiplying this one by this distance, you can get the moment under the 50 kN load, which will be your maximum moment. Now, we still weren't able to finish this one because we want the moment under the 30 kN load. Now, as we have discussed earlier, we can just use the resultant in order to solve the reaction at A or the reaction at B. Now, to get the moment under the 30 kN load, you can consider the left side, this one, or the right side. Now, so that our discussion will be holistic, let's try the two ways. Now, I'm going to solve RA, so we will take moments about B, and then we have RA multiplied by 12, and then minus, let's just use the resultant, we have minus 80 times the distance going to B. So we have this one. And so this distance is, this is 0.78125 plus 6 meters. So 6 meters and then 0.78125. We have this one. Again, 6 from B to the center line and then plus 0.78125, which is this distance. So RA will be 45.2083. And then we can also solve for RB. We can sum of forces along Y. We have, this is 45.2083. And then minus the resultant, which is 80. And then plus RB. Setting this to 0, we have RB equal to 34.7917. Now we can actually cut the beam at this point because we want the moment, the maximum moment under the 30 kN load. Now if I will consider from the left, then the positive effect will be counterclockwise, while for the right side, the positive effect will be clockwise. Now this will be important. Both of these would be the moment under the 30 kN load. Now if I will consider from the left side of this cut, then I have, let's say this is M30, then we have this load, so 45.2083, and then minus 50 times the distance going to the 30 kN load. So we know that this is 2.5. And so solving this, we have, by the way, we are lacking the moment arm for this one. This is from here up to the 30 kN load. We have a distance of, this is again 6 meters plus this one. This is 0.78125. So times 6 plus 0.78125. And then again minus 50 multiplied by 2.5. So we have here 181.569. And then this is KNM. Now you may also use the resultant force instead of 50. And so if we're gonna use, let's erase this one. Let's try to use 45.2083 times 6 plus 0.78125 and then minus 80. Let's use the resultant instead. And then this is multiplied by this distance, 1.5625. So we have here, now again, this is 80. We still have 181.569. And so our results are the same. Now using the resultant force will be helpful if you have 3 moving loads, because you will only need to use 1 load. Now sir, what did you mean earlier that we have 2 ways? This is not what I'm referring to. What I'm referring to is you can solve the moment under the 30 kN load considering the right side so that our solution will be more efficient. Now let's try that. We have here the moment under the 30 kN load, that's clockwise. So we have M30 and then this must be in equilibrium. So summing up moments considering the right side, it must be equal to 0. So we have positive M sub 30 because this is clockwise. And then we have minus the reaction at B, which is 34.7917. And then we're going to multiply this by the moment arm going to the 30 kN load. And so that distance will be 5.21875. So 5.21875. Setting this to 0, the moment under the 30 kN load will be still 181.569. And then this is KNM. And so as you can notice, the result is still the same, but we only used a singular force. Now instead of doing this one, you can also take moments about this point and then just change the sign. Because if you will take moments from the right side, the convention will change. Now earlier, we directly took moments about the 30 kN load considering the left side because there will be no changes in the convention. But if you're taking moments from the right side, always remember that there will be a change in the convention because of the positive effect of the beam. Now if you want to learn more about this concept, you may look at our video on the shear and moment equation. Now, if you don't want this one, another way is to mirror the loads. You can exchange these. And so the 30kN load will be right here. And here we have the 50kN load. And then you can solve for the moment under the 30kN load just by solving RA. And then you will still get the same value of 181.569. That solely depends on you. But take note that if you will mirror the loads, then you must also mirror the distances. Now, I actually have a program in MathCAD that will be able to check the maximum moment under a given load. Now, let's say we have 50kN as the leftmost load and 30kN as the rightmost load. As you can see here, we have 73.75 and we also have 203.96, which was our answer earlier. Now, if we're gonna change this one, let's say this is 30 and this is 50, the maximum moment will now be 181.569. So this is the same earlier, and so that's how we can verify that our answers were correct. Now I will be teaching how to form these equations when I will be able to handle numerical solutions. And so this is it for now, and then for the next videos, I will be discussing more examples which will cover the complicated cases.